successful stories for like young researchers and for the center that you have established here. I don't think I have more information to add, but this is just a humble story about my way. So I refer all the success, and this is something that I want every young researcher to think about it day and night. All the success that you will have in your life, you should refer to the foundation and the moral issue and the teaching of your family, your professors here in Egypt. Because I would say that we can compete for the bachelor degree that you study here in Egypt. And like I started at Ain Shams University, and then I had my PhD from the University of Massachusetts Amherst, and then I had a chance to work there as a scientist, as a Jeff professor, and then University of Rhode Island, University of Braunschweig in Germany, and then University of Michigan State University. That was my last step, and then I came back to meet with you here. Challenges. I would say challenges in the beginning. It was like something related to the cultural barrier and also related to the educational barrier, because as our professor here mentioned that we have somehow to reshape the education here that you receive from the university, and to change the way that you think, not to just too much information in your brain, but you have to be trained about how you think about it, how you use your brain power. So from the tradition to the advancements to the innovation. So the traditional way of thinking and the traditional way of doing research here, this is something old-fashioned and it has to be changed. Background. I started here with the way we detect by microorganisms 18 years ago, 2 years ago. It was used like selected media, but it doesn't tell you much information about the microorganisms that you deal with. After I went there, so the challenge was to learn immunotechnology. It was something like ELISA, it was like this during the year 1990, 1995, it was something new. And then genotyping methods. So like immunotechnology-based methods and DNA-based methods was something advanced at that time. But nowadays, it became like a standard methods. And the big move now is to bring the whole laboratory. Like if you go to any lab, so you look at all these equipments, you bring all of these equipment into a small chip, something at the size of your finger. And this is what is called biosensors. So I started there as a molecular biologist, developing methodology for molecular techniques for the detection of hazards in general and in particular foodborne pathogen. And this is part of my contribution. And then when I came back to Egypt, I would declare out loud that in Egypt here, the most important issue that we deal with for analysis is the expenses of the lab equipment first, and then the reagents, and third, to have trained personnel. So the reagents here, I haven't seen a big move to produce the reagent that we need in our country. For example, if I have a microbiologist here and I ask, if you bring in a reagent or any detection like kits from abroad and try to detect your own the bacteria, E. coli 157 or Salmonella or and so on, the antibody is not going to be that specific for your local strain. I did that. I was at the University of Massachusetts Amherst, so when I developed my own antibodies, the antibodies I got was more specific, and also it was cheaper, and you can create your own identity here. So from my experience abroad, I believe Egypt needs a national project to develop and produce our own reagents in all molecular techniques. This is not something hard. We have pioneers, we have scientists who can do that job, but we need an effort and we need collaboration. After that, I was lucky to join a multidisciplinary group a multidisciplinary group. And it is unfortunate to hear that within one college, we don't have collaboration. We don't have collaboration within one college. I had that chance to work with different 7 majors, multidisciplinary, like from the School of Engineering, and from computer science, and from imaging analysis, and physicists, chemists, pharmacists. All of these, and molecular biologists, all of these, they collaborate to develop biosensor. What does this mean? To bring the whole entire laboratory in a small chip, which is called lab on a chip. And this is a biosensor. This is lab on a chip. So lab on a chip, as you see here, I don't have a pointer, so I don't know how to use this one. So you have here biosensor. It consists of biorecognition elements and transducer. Biorecognition elements where the molecular biologist will work hard with with mechanical engineering to develop a smaller chip to be able to have this one. So this is the recognition elements where you have the biological analytes attached to this place, and then you use the transducer to read this signal, and then you have the readout. So now you have a small chip at the size of this, something that you can carry in your hand, and this is going to be your laboratory. You carry your laboratory wherever you go, and can allow you to detect whatever you want. So can we establish a facility here in Egypt to do such a thing? Yes, we can. Yes, we can. And every physician can have this facility at his clinic. Not to wait for sending samples to the lab and then coming back and blah, blah, blah. And also this is going to be something very cheap. So in the beginning I said the expenses that we look at, first equipment, second reagents, third personnel. For biosensor, you don't need skills. So because I had 5 graduate students, and at the end of their project, I had to invite undergraduate students, sophomore, second year or freshmen, and ask them to apply this. If it proved that it can detect, I would say your work is fine, and your work is good, and now you can defend your thesis. If it didn't work, I say your work is not good, and you have to repeat the work again. So we can cut all of these expenses by having a national project to produce all the reagents that we import from outside for billions of dollars. Trust me, for billions of dollars. I have checked that with the Ministry of Health, with the Ministry of Agriculture, they spend lots of money for that. And also, instead of the equipment that is very expensive also, you can have a small equipment, something very small, which is called lab on a chip. As you can see here, these are the, so first you have the bioreceptors, transducers, amplifiers, signal processing, and recording in the readout. So this is to prove to you that you cannot do this research by your own. You can't do that. So you have to collaborate. So here in Egypt, all the universities, we need to establish a multidisciplinary programs, a multidisciplinary academic programs, a multidisciplinary research programs and projects in order to understand how to reach to an innovation. Because the creativity, the possibility of having a creativity when you do research with multidisciplinary is much, much higher than the way you do it when you dive in and you dig into your small thoughts and small ideas. So we need to talk to each other and to understand how we get benefits from each other's expert. For example, yesterday, someone came to me and she has something unique chemicals that can be anti-cancer, antimicrobial. But because she doesn't have collaboration, she's a scientist at the School of Women, and because she doesn't have access to somebody else, so she does all the work by herself. She has to learn how to deal with rabbits, and in order to test the products, like the chemical that she prepared. And also, she has to use microorganisms, even though she's a chemist. So she will not be able to do it, right? So after I heard that, I contacted Dr. Hind and myself, microbiologist, and inshallah we're going to form collaborative research among us. I'm trying to go very fast because I know time is limited. So this is to show you that in the world market now, there is a big move toward lab on a chip. Lab on a chip. And the growth rate is 15%. And it's going to be like $3 billion in the market this year in the United States. How many companies are working worldwide? 269 in 31 countries, 35 contract research organizations, 118 university research group worldwide. Did they have some products already in the market? Yes, they have some products in the market, as you see, to check about sensors for foodborne bacteria and for monitoring pathogens and for animal pathogen testing and detecting bacteria in oyster industry. How to manufacture lab on a chip? This is something I would say you make and you design and you build your laboratory in a small chip starting from scratch. Start from scratch. Like if you want to use PDMS, this is something like plastic. So you have everything start from scratch, and we can do it here in Egypt from different materials. This is something that I have already published, ultra-fast quantitative heterogeneous immunoassay on pre-functionalized PDMS microfluidic chips for next generation immunosensor. So when I joined that group, it was funded by National Science Foundation between University of Braunschweig in Germany and University of Rhode Island in the USA. I told them, guys, we need something that you can keep in the market. So we need to test the pre-functionalized chip. And it was really successful. It went through 3 months without any defect. So you can have a chip that you can keep it in the fridge or in the market, and then you can use it at any time. And this is the size. This is the size of the chip bagged in this box. And this is the 3-dimension of the way it is functioning. If anybody is interested, so you can discuss this with me after my presentation. Now, people here, they deal with PCR. And they know how hectic it is to do the gel electrophoresis after we have PCR amplicons. So we have designed a smaller chip to detect PCR products for it took around 10 minutes without looking at all of this hassle. And this is the first one that was published to detect PCR products. This is the way we did it with what is called immuno-PCR. And this was 100 times more sensitive than the gel electrophoresis, as you see here in the figures. And then I have tested that with ground beef as well. With ground beef, it was able to detect 5 cells. However, agarose gel electrophoresis failed to detect 50 cells. And this is something very unique. I know that also you are familiar with ELISA. This is something. Okay. ELISA, it depends on, you add something and you wash, you add and wash, you add and wash, you add and wash, you add and wash. And at the end, you get the read out with ELISA microplate reader, right? So we had a smaller chip to do all of these jobs. As we say in the United States, you set it and forget it. You set it and forget it. How? We have developed a portable pumpless and valveless micro device for detection of biological analyte free of instrumentation, without any instruments. So we have here, this is how the system is working. We have to do encapsulation channels, and then to have mobile phase and stationary phase, and this is how the system is working. So you have the magnetic beads carrying your target, and then it goes from aqueous phase to oil phase, aqueous phase to oil phase, aqueous phase to oil phase, and then we have all the reagents here inserted. So it goes here, so it attached to what? To the binding buffer. and then here enzymes, and then here washing, and then at the end you have the substrate and you have the read out, and then you can read. So you set it and forget it. So this is something to show you how ELISA is working. This is more work that was done. You can just look at it this way. More work, and this is the current work. Now I have proposed a micro PCR, a small chip, to detect, like to do the amplification, and to allow you to see the results in the chip. This is for extraction of like from blood samples, and paper paste microfluidic. Like you do it, you can fabricate that from just membranes. And then at the end, you can have a detector like this to detect multiple analytes at the same time. Thank you very much.